Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Layer 4 of the OSI model is known as the transport layer, and it plays a critical role in managing the delivery of data between hosts. Positioned between the network layer below and the session layer above, Layer 4 ensures that data transferred over a network arrives accurately and in the correct order. It is responsible for segmenting messages, tracking transmission, and coordinating the flow of information between devices. Without the transport layer, reliable communication between endpoints would not be possible in complex multi-hop environments. This layer is tasked with several key responsibilities that support the integrity and efficiency of network communication. These include handling connections between devices, managing data flows so that systems are not overwhelmed, and performing segmentation and reassembly to break large blocks of data into manageable chunks. Layer 4 operates in the background every time we send a file, stream a video, or open a web page, making its mechanisms essential for everyday connectivity. The transport layer is where true end-to-end communication takes place. While Layer 3 is concerned with moving packets between networks, Layer 4 focuses on host-to-host interactions. It ensures that data sent from one application on a source device is delivered to the correct application on the destination device, maintaining an ongoing conversation between the two. This operation is carried out independently of the path the data takes, which allows for flexibility in network routing and reliability in service continuity. A key function of Layer 4 is the segmentation of data. Large messages generated by applications are broken into smaller segments that can be transmitted efficiently over the network. Each segment is assigned a sequence number, which helps ensure that data can be reassembled correctly on the receiving end. This process also supports retransmission and tracking of individual pieces, creating a robust system for handling data integrity during transfer. At the receiving end, the transport layer reassembles segments using the sequence information provided. This ensures that even if data arrives out of order, the message can be reconstructed exactly as it was sent. The reassembly process is especially important in networks where data may take multiple routes, causing segments to arrive in unpredictable sequences. The transport layer keeps track of all segments and waits to process them until the complete set is available. One of the two major protocols operating at the transport layer is TCP, or Transmission Control Protocol. TCP is a connection-oriented protocol that establishes a reliable session between sender and receiver before data transfer begins. It uses acknowledgments to confirm receipt of data and employs retransmission mechanisms when segments are lost or corrupted. This level of reliability makes TCP the preferred protocol for tasks that require accuracy, such as downloading files, accessing secure websites, and sending email. The other primary protocol at Layer 4 is UDP, or User Datagram Protocol. Unlike TCP, UDP is connectionless and does not perform handshakes, acknowledgments, or retransmissions. It simply sends data to the destination without ensuring it has arrived successfully. Because of its simplicity, UDP is lightweight and fast, making it ideal for real-time applications such as voice communication, video streaming, and online gaming, where speed is more important than perfect accuracy. When comparing TCP and UDP, the distinction is primarily about reliability versus speed. TCP guarantees data delivery, preserves order, and includes mechanisms for managing traffic flow and correcting errors. UDP, on the other hand, sends data with minimal overhead, sacrificing delivery confirmation for lower latency. Each protocol serves different types of applications, and understanding when to use one over the other is a critical skill for both the exam and real-world network design. Port numbers are essential to the transport layer, acting as unique identifiers for services running on a host. Each segment contains a source and destination port number, which, combined with IP addresses, allows devices to route traffic to the correct application. Well-known ports such as 80 for HTTP or 443 for HTTPS correspond to standardized services, while dynamic ports are assigned temporarily for client connection. This addressing method allows multiple applications to communicate simultaneously over a single network connection. Flow control and windowing mechanisms at Layer 4 regulate how much data is sent at a time, preventing senders from overwhelming receivers. TCP uses a sliding window to determine how many segments can be sent before requiring an acknowledgement. The size of the window adjusts dynamically based on network conditions and receiver capacity. By pacing the data stream, flow control maintains performance and minimizes packet loss, especially over slower or congested links. Error checking is another responsibility of the transport layer, and TCP includes features to detect and correct transmission errors. Each segment contains a checksum that verifies the integrity of the data. If a mismatch is detected, the segment is discarded and retransmitted. These mechanisms ensure that the data received matches what was originally sent. UDP also includes a checksum, but its reliability is lower due to the lack of retransmission and confirmation logic. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Connection, establishment, and termination are core functions of TCP at the transport layer. To begin communication, TCP uses a three-way handshake. First, the initiating host sends a synchronization request to start the session. The receiving host replies with an acknowledgement and its own synchronization. The initiating host then sends a final acknowledgement, completing the handshake and allowing data to flow. When communication is complete, TCP follows a controlled shutdown process to ensure that all data is received before terminating the connection, using a sequence of finish and acknowledgement messages known as a graceful teardown. Layer 4 is especially important in firewalls and network address translation or NAT systems. Firewalls often use port numbers to permit or deny traffic based on predefined rules. These rules determine which services can be accessed and help block unwanted traffic. NAT devices, which allow multiple internal devices to share a single public IP address, rely on transport layer information to track active sessions. By inspecting port numbers and session identifiers, these devices can correctly forward packets to the appropriate internal hosts while preserving state and security. Multiplexing and demultiplexing are essential to managing simultaneous connections on a network device. Multiplexing allows multiple applications to send and receive data at the same time by assigning unique port numbers to each communication stream. Demultiplexing occurs on the receiving side, where incoming segments are sorted based on these port numbers and delivered to the correct process. This enables a single host to run many networked services concurrently without confusion, ensuring accurate delivery for each application. TCP uses sequence and acknowledgement numbers to track each segment sent and received during a session. The sequence number identifies the position of each segment in the overall data stream, while acknowledgement numbers confirm receipt of specific segments. If a segment is missing or arrives out of order, TCP can detect the problem and initiate retransmission. This mechanism ensures reliability even over networks where latency, congestion, or occasional packet loss might occur. And the result is a complete, ordered data stream at the destination. The transport layer also contributes to quality of service, or QoS, in network traffic management. Some implementations allow prioritization of certain types of data, such as voice or video, to ensure they receive timely delivery. This may involve classifying traffic based on port numbers or application types, then applying policies that prioritize those packets over less critical traffic. Layer 4's role in QoS supports performance guarantees for services that are sensitive to delay or jitter, such as live conferencing or real-time control systems. Transport protocol headers vary depending on whether TCP or UDP is being used, but they all include essential information for processing data. A TCP header includes source and destination port numbers, sequence and acknowledgement numbers, flags that indicate session control information, and fields for window size and checksum. UDP headers are much simpler, containing only port numbers, length, and a checksum. These headers allow each protocol to encapsulate the transport layer segment appropriately and guide it through the network. The lightweight nature of UDP makes it a preferred option for certain applications. With no need to establish or maintain a connection, and with a minimal header size, UDP introduces very little overhead. This makes it well-suited for real-time services like streaming audio and video, where the occasional lost packet is less important than maintaining a continuous flow. UD's simplicity also supports applications where rapid communication is required, and reliability is either handled at the application layer or deemed unnecessary. Layer 4 responsibilities are often summarized by examining the behavior of TCP and UDP. TCP offers robust control and accuracy, using connections, acknowledgements, and retransmissions to ensure that all data is delivered correctly and in order. UDP, in contrast, offers simplicity and speed by forgoing connections and delivery guarantees. Together, these protocols provide flexibility to support a wide range of networking needs, from secure file transfers to fast-paced online gaming. Their coexistence reflects the diverse requirements of modern applications. The transport layer forms the bridge between raw packet delivery and session-based communication. It enables reliable or rapid data delivery through TCP and UDP, manages port-based service identification, and establishes the flow control needed for efficient transmission. Understanding how Layer 4 handles data segmentation, error checking, and session management equips learners with the tools to interpret traffic patterns and troubleshoot connection issues. For Network Plus candidates, this knowledge is key to grasping how data moves beyond the boundaries of the local network and interacts across the application stack. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.